Okay, so let's begin class. Do I have everyone's homework assignment? This is the brutal snowstorm of death keeping some of the students away, I suppose. So last class we went over this concept of pipeline stalls and data forwarding, right? So today we're going to discuss how that's actually done in the data path. So we had a single cycle data path. Now we have stages in between with buffers in between each stage. And now we're trying to get as many instructions in as possible. We determined previously that through a proof that the ideal speed up is the number of stages, k. And this concept, if you break it into a lot of stages, called super pipelining. So you just try to break it up into as many stages as possible, so that no value of k would go up. In MIPS, the value is 5. Then we've determined that, that's actually a problem in the non-ideal world where we live, because we have these things called pipeline hazards where we're not able to complete an instruction one clock cycle after the next instruction. We have data hazards, structural hazards, and control hazards. And we try to address them using pipeline installs and data forwarding. In last class, we did an example with our makeshift data path and data forwarding unit of how that's done. So now we're actually going to look and see how that's actually done at the MIPS level. So you recall, this is the truth table that we used for the control unit. And we have this basic R format, load word stored, and branch equivalent. This is an example. Now, it's broken up this way for a reason. When we have the control unit generates the control signals, it's going to go to the next. It's either going to send it to the values in that particular stage, or it's going to send it to the next stage by holding it at the buffer. So, control signal generates everything, and it goes past. None just immediately go to the instruction decode stage. Why do you think, for example, reg write is passed all the way back to the write back stage? Why do you think I would want to pass reg write to the last stage instead of have it come immediately? Just remember, from the single cycle data path, there's the controller, and that comes from 31 to 26 from the instruction, right? So the controller is right there, and that's where the registers are. So you'd think it would just make sense to have the register write come in that particular stage. But we have it passed all the way here to the write back stage. Why do you think that is?
Well, other sources are going to have to use the registers as well. And if we take the reg write and we're putting it to the, did you say the fetch?
No, yeah, the fetch stage.
The fetch stage, then I guess some of those other ones would still use the old registers.
You're in the right ballpark. You're overthinking a bit. This is a classic engineer. We tend to overthink the question. I mean, the answer is in the question. Why do I want the reg write in the write back stage? When? I want to write when we're actually writing, correct? Mm-hmm. Problem is we have it go to the instruction decode stage. The value they're supposed to be writing back is going to be for the wrong instruction. And if we recall from having these control hazards, we won't want to be updating registers if, in fact, we don't want to be doing that. So let's say it's a store word instruction, and we don't want that value writing to a register, and we just send a reg write immediately. Well, we'd actually be overwriting a register value. So that would be a control hazard. So what we want to do is we want to pass the reg write control signal through the execution stage to the next buffer, to the decode stage, to the next buffer, to the write back stage, and then these two control signals are going to come here. The mem to reg is going to go to that multiplexer that comes out of the data memory, right? And it compares the result of the ALU, and then that value is going to go back with reg write, and then reg write is going to update with the result of mem to reg. And so this is how it's physically done, what I just described here. So we have the instruction coming from instruction fetch, instruction decode buffer. 31 to 26 goes to this control unit, and all 9 control signals go to this buffer. So here, the execution stage, we're going to have ALU source, the two ALU op signals, and we're going to have branch come here, right? Because that's what we're going to be controlling that stage with. The rest of them are going to be propagated to the next buffer. Here at this buffer here, the execution memory buffer, we're going to have mem read and mem write. And also you're going to have jump here. And then the last stage, we have reg write and mem to reg. And so this is what the stage buffers in the single cycle data path kind of look like. Kind of high level view. So we have a multiplexer. We have this value here. It says PC source. We're going to not include that in this particular data path because PC source starts to get into multi-cycle. You're just going to control that by using branch and then jump. But here's the idea. PC plus 4, instruction memory, buffer. Instruction is generated. The control unit generates the buffer here. WB is write backstage. So all these signals that would go to the write backstage buffers come here. So here we have reg write comes here, and then mem to reg. From here, from execution stage, we can see we have ALU source. We have ALU op comes here, and then register destination is the next stage. Why do you think that is? This is where things get a little tricky. Is this required to be here? Let's engineer. What's the pros and cons of having it here versus here versus here? Because the whole idea is we're taking these 20 to 16 to 15, 11. So this is 5 bits, right? So here we have 2 5 bits stored in the buffer. And then they're multiplexed in this next stage here. And then propagated, this is 5 bits. And then this is 5 bits. And then it comes back to write data here.
Well, we have it there because we want it to, we want the reg destination to get there at the same time as the, what is that? Yeah, 0 to 16 and 15 to 11 bits of the instruction to reach the multiplexer all at the same time. Right. So we gotta wait for the control to do its thing.
Right. So if we have a control signal here, that's how it gets there. But what would be the pros and cons? Because let's say I move the multiplexer over here. So for those of you watching the video later, let's say I move the multiplexer here, I had register destination just come out here, and instead of having 2, it's just 1. Here, if I cross here, and then back here, so that's the same thing, right?
Less wires.
So you have less wires, but what's the drawback? Not stall. This is a little nuance there. I'm just telling you that just because you see something drawn up here doesn't necessarily mean you have to do it this way. So here, you have all the buffers together. Here it would just kind of come across and be down here. So you have a trade-off of 1 buffer, 5 buffers, but you're not necessarily keeping them all together. They just made this design kind of keep everything together. They wanted the control signals to be generated and put everything here so that way, to kind of get to what you were talking about earlier, the timing. You could get it all here. Everything just put out. You have the buffer here. You insert the delay, and then it comes up to the next buffer. Right? Bless you. So putting it over here in the next stage would mean you have to have 5 more buffers here, which isn't really that much of a trade-off. We learned about tri-state buffers, right? So just 5 tri-state buffers, so it's not a huge cost, but it's still a thing. But here you can do that and just have it come all the way back and not have to worry about any other types of hazards. But on exams, if students have put the multiplexer here, it's not been a big deal. As long as you can justify it. And so in order to do all of this, we're going to talk about something called a hazard detection unit. So we talked about a data forwarding unit, which takes in the inputs, which takes in the actual current values, the 5-bit values from the registers, compares them, sees what the most recent value is, and checks, and then puts the most recent value on input multiplexers, which are not in this current diagram. The hazard detection unit is a control unit used to determine if one or the more pipeline hazard conditions exists in the data path, and inserts install if one exists. So TGO 6.22 is the comparisons that the data forwarding unit, the hazard detection unit does. So ex underscore mem dot register RD, that means the execution stage here, right? So this is RS and RT, right? And RD is the result. The RD is the result from the ALU is compared to ID execute register RS. What that means is we're comparing the result from the ALU, that's what register RD is, the destination register. We're comparing the result from the ALU from the next instruction with the input value here from RS. So what it's going to say is like, hey, is this more recent? Is that register there? Here? Yeah. By doing that, you can say, oh, if this is the most recent copy, we can put that value here into the ALU instead of this value, because it's the least recent copy. And if it's not, correct. Mm-hmm. If you recall from the last example question we did, where we have to wait, and that's where these last two portions of it come in. If we have to wait from when it comes out of the data memory, a stall is unavoidable, even in pipelining with data forwarding unit. So that's how we get there, because when you do a load word instruction, the value that we're going to be loading into the registers does not come physically into the data path until it comes out of read data. And then it's put on this buffer here. Does that make sense? Previously, if we're able to do it here, then we can just have it go immediately. But here we had to insert a stall because we had to have a whole nother clock cycle where we had to wait until it was put on the buffer. And once it's put on the buffer, then here what we would do is we would do mem write back RD is compared to RS or RT. So these are what these two bottom ones are. So these top two are execution RD, that's the output of the ALU, is equal to IX ID/EX, that's the input from this buffer here on this register. If we look at this register here, this is IFID, instruction fetch, instruction decode execute, ID/EX. So that's what this means, ID/EX. That's the values coming from this buffer going into the ALU here. So the reason why all these four on the right are the same is because the hazard exists if the values coming from the registers aren't the most recent copy, which means we either have a more recent copy here at the execute/memory buffer or the mem/writeback buffer that's coming out of the ALU. And the other instance would be, what happens if we have an add instruction where we're updating S1, and then 2 instructions later we need S1 again, right? So we would update it. It'd be 1 instruction later, it would be here, but we don't need it yet, right? So the comparisons would just pass the values from the register. But we get to the next value in the ALU, well, I need it back here, right? My most recent copy's here, so I need to forward it back. That's why, if you remember from that example, that's why this hazard is also a hazard with the subtraction value. And that's why this T5 here is a hazard with that T5. Because that's physically a case where that hazard's met. And the data forwarding unit, as I've alluded to a number of times, is the unit that actually takes the physical values from those buffers and forwards them back to the arithmetic logic unit so it can use the most recent copy.
Data forwarding unit in each buffer?
No. No, there's one data forwarding unit that's taking the values from both of these buffers and comparing to see if there's a hazard, and then sends them back to the ALU.
Where would it be implemented on that design? How would it be implemented?
Like this. We'll get there in a minute. To be answered soon. Okay, so this is not part of the topical guide objective. That's data forwarding unit. Let me read that again. A control unit which takes inputs from the control signals at each stage and forwards the values to the inputs of the ALU. And so here's kind of how it's implemented at a smaller level. So we have the values coming out of the buffers, right? So this value, this value is coming to ALU, right? And it's being sent to the inputs of both multiplexers, right? So we're going to have two control units, control signals called forward A and forward B. Forward A is going to do the input to the RS input of the ALU. Forward B is going to have the input to the second bit of the ALU. And it's going to also have data memory, right? The multiplexer is coming out. And it's also being sent to the input of the multiplexers on the ALU, right? So the forwarding unit also receives the 5-bit values from what the actual values are. So what's happening is it's being forwarded to the ALU, but the forwarding unit is receiving the 5-bit value indicating the actual register. So it's comparing and saying, is this input to the ALU the same as the register that I'm intending to write it to? If it is, actually I want to use this one. This is the most recent copy. Is it this one? If it is, I want to use the most recent copy. And what happens if I have 3 instructions where I'm updating the same value? Then I would make a comparison here. And obviously I would want to use this one because that's the most recently updated value. And so here's how the control signals to these multiplexers are done. Forward A, if it's 0, 0, the source is ID/EX. That means it's just taking it from the ALU. The first ALU operand comes from the register file. That means it's coming from read data 1. Forward A is 1, 0. It's coming from execute/memory. So this is from the output of the ALU. It's been put on that buffer, and it's going to be propagated to the memory stage. So the first ALU operand is forwarded from the prior ALU result. So what that means is it's taking the result from the ALU, it's at the buffer, and it's been forwarded back to that multiplexer. Forward A01 means that it's coming from the memory write-back stage. So now we've gone past the ALU, and now we're at the buffer between memory and write-back. So the first ALU is forwarded from the data memory or an earlier ALU result. So which control signal would compare these two? From the data memory or from an earlier ALU result? Which control signal does that in the data path? No. What control signal? There's 9 control signals: read, write, memory, memwrite, ALU op, ALU source, branch, jump. And the one I'm leaving off deliberately because that's the one I want you to tell me. If I'm having a control signal comparing the value from data memory or from the ALU, an earlier ALU result, what's the control signal that's used to do that? It's right on the tip of your tongue, isn't it?
Yeah, I missed the question again.
The question is, what control signal in the data path that we've already studied is going to compare the value from the data memory or from a previous ALU result? So the values come from the ALU. It circumvents data memory. It comes out of data memory. There's a multiplexer there. No, not branch. And there's a control signal. Which control signal is that? Not register destination. Register destination compares which one I want to write to. This is actual physical values here. If I want to take it from the memory to the register, or from the ALU to the register, which one do I want?
What type of instruction?
Well, any type of instruction. I want to take it from the memory to the register, or I want to take it from an earlier ALU result. Which control signal do I want? Well, what was the question I just asked?
What are the LU ops or?
If I want to take it from the memory to register, or there you go. See, not a trick question. It's there. Remember, the control signals are named for that reason to describe what they're doing. So you're going to take that result from this mem to reg. So that's what's going on here at this multiplexer. Mem to reg is taking it. So if it's coming from the memory to the register, that makes it a 1. If it's coming from the ALU, right? It's going to be a 0. That means it's not going from the memory to the register. And it's going back to the ALU. So it's going to take this value and see how it's putting it as the inputs to multiplexers here. The forwarding unit is then going to put this control signal. So let's say that the result is actually going to overwrite. We want that to be our second input, right? So we want forward B to be activated, and we want that to be mem write back. So that's control signal 0, 1. So forward A is just which one do I want, which of these 3 do I want at this input, and forward B is which one of these 3 do I want at this input. Does that make sense? What's the control signal that takes it from the data memory to an earlier ALU result? No! Mem to reg, there you go. Reg to reg. That sounds like a very cheesy sitcom that's coming up on Fox or something like that. Starring Kevin Spacey or something like that. Okay, so this is the full pipeline data path. So this, so a couple people have already noticed this, I've actually posted this as a PDF on Blackboard under content. So look for TGO 25, the whole thing is there, so you can go through there. Okay. This is an advanced digital system, right? What's the class called?
Reduced advanced.
Well, if you wanted to reduce class, you can get a reduced grade. It's not funny until it actually happens. No, what? What do you mean I'm 2 credits short of graduation? Reduced advanced digital systems, you get 1 credit. All right, so.
Teach me about control.
Well, there you go. There's the control right there. So let's walk through this. Program counter, right? PC plus 4. Now, we have the buffer here. This is IFID, right? This input here, that's hazard, HDD. The hazard detection unit tells me whether or not something's actually happening. If it is, we insert a stall. So that's how it's physically happening. Stalls are inserted in this manner, right? So then, PC plus 4 comes up here. See this? Concatenation, shift left 2, 28, 32 bits, that's jump, right? So now we know how our jump's being done. So we have the instruction coming out. 25 to 21 goes to read reg 1. 31 to 26 goes to our controller. I've included our hazard detection unit, at which point it has I call it HCD coming out. Reg write, I see I've made a note here from mem write back. I don't expect you to draw all this because it's a little too complicated. We'll explain. These are write register and write data that's coming back from the write back stage. You see here at the bottom, right? So here we're just at the registers. 25 to 21, 20 to 16, come here. Notice how 20 to 16, we have our multiplexer here to compare register destination. We go to this buffer. You can also get full credit by having these 2 values come to the buffer and performing a multiplexing here. We use a comparator here to go straight for the branch. And then RD1 and RD2 are put onto the ID/execution buffer. Okay. Here, this control signal also has all 9 control signals go to this hazard, right? Now, remember I was talking to you last class about what happens if we actually have a hazard when we need to insert stalls and all the control signals are 0? Well, this is how it's physically done. It's physically done by putting a 0 here as a multiplexer. So you have a 18 to 9 mux, where if it's 0, if there's 1, there's no hazard. If there's 0, that means we've encountered a hazard in the data path that we require a stall. So then we just put zeros on everything, so that way there are no more, nothing more is done through the data path, right? We have our 15 to 0 sign extension that we would be using for branch and for immediate instructions. We also have the 10 to 6 coming through for our ALU, and 5 to 0 for our ALU control. So we're going to also be sending to the data forwarding unit, we're going to be sending all of these values from 25 to 21, 20 to 16, and 15 to 11, right? And the reason why we're sending those values to the ALU is because we want every instruction to say, this is our current instruction, and these are the previous instructions. And so those are going to the data forwarding unit. Does that make sense?
So does
Yeah.
each buffer have a hazard detection unit, or is it just the?
Because the reason why it's here, this is a really good question. The reason why they're here is because by doing this, we're waiting until the hazard is cleared to put in a new instruction. So the way the hazard's cleared out the rest of the way is putting zeros to the rest of the data path, so nothing's actually physically done. Because I'm going to go over that again. This is an important point. The reason why this hazard control signal here goes to the IFID buffer and the program counter is because there's no control signals here, right? So in order to ensure that a stall is put into the data path and to ensure that we're not doing improper operations, we need to actually tell it to not propagate any signals until the hazard is cleared.
And the one under control, what is that actually? The one under the control unit you have, what is that one?
That's just hazard detection, and anything that says HCD, hazard. Yeah. That is meant to reduce the, I don't want you having to draw everything because it can get really confusing. So now we get to the execution stage. We get our values from the data forwarding unit, as well as the actual physical values themselves from the output of the execution stage and the output of the data memory stage, right? So we use that from the control signal results from the topical guide objective, so you know which one. 0, 0 comes from the ALU. Here we also have ALU source, right? So we're still choosing whether or not it's an R-type and I-type. So if it's an I-type instruction, we want ALU source to be 1, and then we want forward B to be 0. Forward B would always be 0, 0, because there would never be an instance. If it's an I-type instruction where we're doing add immediate, where we'd be having a second register value coming back because it's an actual integer value. Whereas if it's an I-type where we're doing a comparison here, the branch comparison is already done. The ALU result receives a value from the ALU control, and that value is put onto the execution memory buffer. We're also getting the memory control signals and the write-back control signals, right? Here we get from memory, in data memory, we receive the read address from the ALU. This value also circumvents and goes to the write-back stage. Additionally, it also splits off and goes to the data forwarding unit, so it can be forwarded back to the ALU if need be in the event of a hazard. Write data here, just like before, it comes from read data 2. Here it comes out of the ID execution stage, splits off, goes past the ALU, hits the execution memory buffer, and then goes to write data. We have memory to memorize control signals, and then the output of the ALU is put on the buffer in addition with the output of the data memory. This 5-bit value here is our result of register destination, right? So we have that 5-bit, which the value that we're going to write to comes through here and then goes through to the write back stage. At the write back stage, we have memory to register. This value comes back. Memory to register tells me whether or not I want the value from data memory or I want the value from the ALU, right? Both of those values are sent back, and that is what comes back here. Write data and write register. So, does anybody have any questions about this? Other than why God, why? To include an industry quote, I didn't put Ransford, I guess I didn't put Ransford's name. When I was interviewed at Intel, they asked me to review the MIPS data path from the architecture of Patterson, Tennessee. When I got to the interview, so he studied the single cycle question, and they said, all right, you know single cycle, break it up into pipeline. So they asked him in the interview to draw this.
Not the guy getting points for like being halfway there.
We got the job, so he must have done well enough. If he didn't get the job, I probably wouldn't put his quote in the lecture stream. Like, well, I went to the interview and I didn't do a good job. All right, well, let's find somebody who did get a job and let's ask for their advice. So you guys, we could have designed this ourselves with the knowledge we had before, right? We knew the single cycle implementation. We knew that we wanted to ensure timing. This is one of the reasons here. This, and when we get to I/O, is another reason why I'm so adamant about ensuring that you have proper timing in your VHDL design. Because eventually, when you get to I/O, we're going to have this concept called debouncing, where clock signals are going to read from I/Os if they're doing something called polling interrupts, where they're going to polling interrupt. The idea is that I'm going to ask you, do you have anything for me? 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 And if you don't have, let's say you're using a keyboard, right? And you're holding down K, and you see how eventually it'll just go hey, a number of times. The reason why is because that's the clock signal coming by. So Thomas is my keyboard. I say, hey, do you have something? And someone's just holding it down. He's like, yeah, I got something. Still got something. Still got something. But if you don't time it right, what's going to happen is I may ask him too fast. So if somebody just presses it once, and all they want is K, but if I ask him, do you got something, do you got something, he's going to say, yeah, I still do. Then you're going to get 3 or 4, 2, 5, depending on how long how far off the timing is. And you try doing a keyboard project where you're just typing something and it gets frustrating because you have no idea why it will only accept it once because you didn't properly debounce it because of improper timing. So timing says, all right, I have something from the instruction memory. I want to make sure that the value from PC+4, all that hit there at the same time, right? I want to make sure that all these values come out at the same time, right? So that way I'm not overrunning things so I don't get improper values. So you know where in the stages where the breakups should be, so you just put buffers there, right? So we've inserted our buffers. Then I know, all right, now I know that I need to count for hazards. We talked about hazards, so there's problems, right? So I have my hazard detection unit. Well, how do we physically take care of that? Well, the easiest way is to just make zeros for everything. I don't want to write to the register. I don't want to write to the data memory. I want to read from data memory. I'll make sure just all zeros to flush everything out. Okay, you've got all this done. But what about instruction memory? Instruction memory isn't controlled by a control signal, right? And it's still, every clock cycle, it's going to put out PC+4 until I want that taken care of. So I'm going to use this hazard control signal to take care of that. Sense? So the last thing is, well, how can I improve that speed up? So remember that problem we did at the end of lecture where it was initially, okay, ideally it's going to take me 7 cycles. Well, if I have to insert stalls, it becomes 14 cycles. So I lose half of the effectiveness of the pipeline. Well, how can I speed that up? By using data forwarding. Well, that incurs hardware overhead, right? Hardware overhead, well, I got to get stuff from the ALU or from the actual data memory, because there could be possible places where I have results, right? So you take these results, you put them back to the ALU, so that way you can use those values before you even have the ability to write them to the registers. And we've already done branch and jump because we know that eventually we need to be able to branch past some instructions or jump back to a specific instruction. So we account for that in our data path. So we now have, we can just do the next instruction. We can branch, we can jump, we can do arithmetic logic unit. I've accounted for hazards. I can do data forwarding. I can go to my memory hierarchy. We learned about set and fully associative memory. So this is where we go to deal with cache, right? And I've got my ALU controller, the ALU, multiplexers, comparators, sign extension.
Yes, you have 25 to 21 going to the data forwarding.
Mm-hmm.
Why is it that one and not like 20 to 16?
There should be all three of them.
Okay.
Yeah. Yeah, that should be 25 to 11. Yeah. Because it should take 25 to 21, 21 and 15 to 11 for write data, because it wants to compare which values we're going to be writing to. And here, this last multiplexer, I should say 0, 0, is what happens when branch is 0 and jump is 0. 0 to 1 is what happens when branch is 1. And 1, 0 is what happens when jump is 1. 0, 0 is branch is 0, jump is 0. So for those of you watching on the video later, 0, 0 is branch is 0 and jump is 0. 0, 1 comes from jump, so that's jump is 1. And 1, 0 comes from branch. It's controlled by the branch, so 1 and 0 is if branch is 1. And that determines what our next program counter is. So this is on Blackboard under content, the TGO 6.25. Does this make sense? As much as it can in 20 minutes. Does anybody have any questions about this? All right. So now we have all of this. So now what's our next problem? We now know, remember we studied earlier in the lecture, in the class about these concepts of exceptions and interrupts, where an exception is an unscheduled event that disrupts program flow, and an interrupt is an exception that comes from outside the processor. So I want to say here that the reason I included this TGO 6.26 is that in industry, in different places, there's different definitions of what they mean by exception and interrupt. There's no hard and fast definition. So for the case of this course, these are the two definitions from talking about objective 3 and talking about objective 4. And it emphasizes the designers of MIPS chose to differentiate between them by differentiating from the internal and external. So internal, meaning what happens in the case where the instruction memory generates an opcode that isn't actually there, right? So let's say we have this whole green sheet, but it doesn't cover all 64 there's not 64 possible opcodes, right? A lot of them, every R type is 0, so all the R type instructions are all 0. So there's not actually 64 different opcodes in your controller. So what happens if, for whatever reason, your compiler screws up and gives you a bad instruction? You have to account for that. Since it happens inside of the data path, that's defined as an exception. And it disrupts the program flow because we don't know what the instruction is going to be, right? The interrupt means it comes from outside of the processor. So an interrupt would be, I have a mouse and I'm saying I want to scroll down. Well, this is sending something to the processor in the laptop to say, hey, we need to scroll down here by indicating which values we actually want to be sent to the screen, right? So all of these, there's all kinds of I/O devices. I have an I/O for my USB, which contains the actual file. I have an I/O, which is for the mouse, right? I have an I/O for the keyboard. I have an I/O to send it to the actual screen, so that way you can actually see it on the screen, right? So the coprocessor is constantly being interrupted. The processor just takes code and does every input and output. So that's the reason why knowing this is important, is because then you can take your compiled code, put it into instruction memory from the operating system, perform page swaps if we're doing different programs. So let's say I'm actually running to the VGA table. I want to take what's currently here in the local registers, swap them out, do a page swap, perform a different set of operations that communicate to the screen, right? Swap it out if I want to do a keyboard operation, swap it out if I want to do a mouse operation. This should be able to do all of those things. That's the whole point of this data path here. This is your actual computer processor.
Do you know how many registers just a standard form ATX board would have?
Standard form ATX board? No, not off the top of my head.
Or just any board?
That's a good question. A standard board. I could keep asking what you mean by standard board all the time, but like you could have 64 to 128 registers depending on the processor. I'm thinking back to the design automation conference where they have these boards that have like 20 processors on them. So I'm like, you could have hundreds if you really wanted to. But if you're just doing the board like the Vertex 5 board or the Nexus boards, I'll probably think 128. 64 to 128. Yep. Well, you have to bear in mind, as we're talking about I/O. The I/O device requests is an external interrupt. The user program invokes the OS. So that's the case where, and we'll discuss this in a second, where you're actually saying, hey, I have some sort of interrupt. I got bad code. I need to tell the computer. So when you have a blue screen of death, right? And it has these two hex values, right? And like, what the heck do these mean? Well, one of those values, we're going to talk about this, something called the exception program counter. That's the exact value of the program counter that occurred when our error took place. So it's telling you where in the program counter the processor was when the error happened. And the second value is actually going to contain the actual error itself. So, and we have two types of things. We could have arithmetic overflow. What happens when we generate an overflow in an addition or subtraction instruction, right? And an undefined instruction, as I alluded to earlier, is the case of what happens when we have an opcode that doesn't actually exist. What happens when the compiler makes a mistake? So MIPS includes a register called the exception program counter to contain the instruction that caused the exception. So this is the instruction where things went bad, right here. That's one of your hex values that comes up on your blue screen of death. The basic action is upon receiving an exception, the processor must save the address of the, quote, offending instruction in the EPC and then transfer control to the operating system. So what's going to happen is, and we start getting outside the scope of the course a little bit, It's going to throw it up to the operating system, and then a bunch of magic stuff happens that you learn about if and when you take operating systems, and then it's going to give you back control of the value. I'm sorry, the data path, right? Eventually, you're going to get the correct value put into the data path, into your registers, or into your data memory. Perform a series of load and store operations. Because we're not going to really go into this much detail in this course. What's happening is the operating system is going to take all the values from your current register and swap them out of the register. It's going to perform a set of store operations, and then it's going to check to see how it can fix the exception.
So is that considered a flush?
No. Flush is what happens when you just flush the control signals out. This is actually swapping all the registers out. Okay? So he's going to store them into the data memory, and then once the exception is fixed, let's say I got to fix this particular instruction, or I got to fix this particular value, then it's going to take them and load them all back in. So it's going to all 32 registers. And to get back to your question earlier, Tom, it's one of the reasons why you have to kind of limit the number of registers, because that's the fast cache, so it's expensive. And when you have exceptions and interrupts, you have to do all of these load and all of these store. So you kind of have to be very judicious with your use of registers. So here's how it actually gives control to the operating system for 6.28. The exception type, if you have an undefined instruction, it's actually going to go to the program counter 8000000 hex. And it's going to go all the way down. So your instruction memory only had 128 instructions. You're going to have a lot more. If you had an exception, if I was to mention and want to make you do this on your project, you would actually have to go down to this instruction, at which point that's a set of instructions incremented with PC+4 that are done to coordinate with the operating system. Now that's why we need to have an error program counter, because it's going to go all the way to the saved instruction, which indicates what we do in the event of an exception, and perform a set of operations. And eventually we need to go to the EPC to go back to the current instruction so we can continue the program. Because the whole point of this is we need to fix it, but we need to continue the program. For example, let's say if you're working for NASA and an exception occurs in the life support system, right? Yeah, just stop the program, fix it. Can't breathe. That sucks. What happened? I don't know. I didn't save where it happened. Error program counter? What are you talking about? That's silly. Just restart. No, we have to have that happen. And the other case, 800000180 hex is what happens. It's the set of instructions that occur when we do an arithmetic, when we obtain an arithmetic overflow.
Is that just an overflow?
Yeah, you get an overflow from the ALU. So this other value here is called the status register. The status register indicates, it's not something we got objective, but the status register indicates whether or not you're actually doing normal operation, or it's given control to the ALU, to the operating system to handle an exception. Let me scroll up a little bit so the people in the back can see 6.28. So the status register includes a register that holds a field indicating the reason for the exception. So when you see your blue screen of death, you see the error program counter value, and you see the value in your status register. Those are those two giant hex values. And vectored interrupt, the address to which control is transferred is determined by the cause of the exception. So we kind of see an example here, right? And there could be, in more complicated data paths, there would be more complicated examples of vector interrupts. But here, this is basically saying, well, if we have an error, there's a specific error instruction that we need to go to in order to address that. Does that make sense? So what we're going to do next is we're going to go through kind of a 6.30, how it's handled, and then we're going to go through a small example of how this is done. So 6.30, the exceptions are prioritized in the data path at any given cycle. So the challenge is to find which one we want to get to. So what happens if we get an overflow at the exact same time that the previous instruction in a pipeline data path gives me an unknown instruction? So to go back to 6.25, here's where this worst case scenario takes place. Our ALU here has generated an overflow, right? Oh, we have an overflow. Oh crap! I need to update my exception program counter and my status register. But at the exact same time this occurs, the instruction memory generates a bad opcode. Oh, I need to update the exception program counter and update my status register, right? So I have two exceptions in the same data path at the exact same time in the pipeline. How do we handle that? So which one do you think we want to handle first? You are the operating system. You decide. That is correct. Why do you think that is? Bingo. Yeah, both of you are right. Both of you are right. Because it's the first one, right? If this is the first one in the set of instructions that is broken, we need to fix this, so that way we can then fix this to maintain the proper operation, right? So the priority, and you'll see this top of that objective, the priority is given to the instructions that happen first. In this case, the priority would be given to the arithmetic logic unit overflow. That would be fixed. And then the operating system would then address the unknown instruction. Does that make sense? So the exceptions are prioritized so the hardware determines the exception to be serviced first. MIPS sorts it so that the earlier instruction is serviced first. Cases where that will not be the case is if we really won't cover such a case in this course, but in multiprocessing where we have to do out-of-order operations, the idea is we are doing instructions out of order to improve performance, but we can still have mechanisms to guarantee that the correct operation is taking place. So if we don't have a hazard or data dependency, you can actually do them out of order to try to make them go faster. The error program counter captures the address of the interrupted instruction, and the MIPS service register reports all possible exceptions in the clock cycle. So the service register is going to say, this is possible? Did it happen? Yeah, it did. Is this one possible? Did it happen? Yeah, it did. All right, well, I'll give priority to the error program counter. Then the next instruction is just EPC plus 4, right? And there you go. So here's how this actually happens. So we have this kind of set of instructions, right? And so if you recall from the top of Brigade objective, here's what actually happens. We have these two vectored interrupts. And what happens is it's going to perform a storeward operation. It's going to take 1000 and 0 this location and store the value of 26. So you guys recall from your spreadsheet with the I just had it here. Which register 26 is? I'll show you where. Oh, there it is. What is register 26? Your next spreadsheet. GP is the global pointer, that's 28.
Oh, GP
Here. Can you read it out? What's 26?
Reserved for OS kernel.
26 and 27 are reserved for the operating system kernel. the reason why we reserve 2 registers here for the operating system kernel is because we have to account for exceptions and interrupts. Specifically in this case, 8084 is what happens when we have arithmetic overflow, right? I mean 8008 0180 0184 is peak C+4, so we're letting these 2 values into the data memory. The data memory then is accessed by the operating system, and then stuff happens, which I won't go into right now. But then we have to deal with stuff going on in the data path, right? We have to perform a flush. So to answer your question, Thomas, here's what's going on. Our control unit interacts with the hazard detection unit. We indicate that there's a hazard, so we're going to flush everything. So we have this value called id.flush. That's instruction decode flush. It's an OR gate. So either there's a hazard or a flush. In that case, where this 9-bit 0, it flushes 0 through the entire data path. And the same thing, because we don't have control signals, it goes back to the program counter and the IFID buffer. And then the flush gets rid of the add instruction, as well as the other instructions in the pipe. So I want to note how it gets rid of everything here, right? But notice how, in this case, this example, the add instruction is where the overflow occurred. But we need to let these 3 instructions complete because we have correct operation, right? So we want to have correct operation there. We want to let those complete, fix this issue, and then continue. So that's why the flush occurs, but the flush goes with the buffers. So the values before, so this OR value is allowed to complete, and the AND instruction before it is allowed to complete as well. So what's going to happen is we perform this store word operation. We're going to get to 26 and 27. Those values are going to be loaded into the data memory to be used by the operating system. And then we have a no-op, and it's going to perform store word, those 2 store word instructions. And then what's going to happen is the operating system is going to fix the issue, update it in the data path, and then it's going to go to the error program counter and say where was the issue. It'll update the program counter to start the instructions at that location, and it'll perform the add instruction as it did before. Does anybody have any questions about that? So that's the end of section 6. Make sure. Yeah, we started at 21. Okay. So now we're going to go beyond the data path, right? So you guys have now, to this point, you've designed your own computing processor, right? So now you know how to do that. So now, eventually, we need to store this memory somewhere, and we need it to be able to run on multiple kinds of processors. So virtual memory is a way of dealing with what happens when the memory that you could possibly store doesn't necessarily match the actual amount of memory you have. So in modern computers, we have 4 gigabytes of memory, and we have dual core, quad core processors, right? Oftentimes, when we were designing computers back in the day, like such as, for example, 1986, when MIPS was invented, you could have 2 to the 32-bit types of addresses for a 32-bit data path, but you really only had 16 kilobytes of memory. So you have to somehow map 2 to 32 to 16K for your level 1 cache. Then your level 2 cache gets a level 3 cache gets a little bigger, and then you deal with RAID arrays. Right? Mm-hmm. Did I bring back some bad memories there? What, RAID arrays? Yeah. Yes, they are. Okay, so we have to figure out how we can use the full technique of the program memory hierarchy in order to determine what the instructions are. So we can load all our instructions in there, and we need to be accessing different portions of the memory. So we have one block holds one part of the instruction, one block holds another part of the instruction. And so what we're going to be calling those at this level is pages. So at the cache level, blocks is the smallest amount of unit that can be transferred between levels of cache. Between the main memory and cache, or to the disks, that's called a page. And so the idea behind virtual memories is a technique that uses main memory as a quote cache for secondary storage. And that's the whole idea of like separating the program into pages and swapping it out to take advantage of that principle of locality. I know it's crazy. So there's two motivations. This is actually virtual memory is actually invented by a student in 1956, Rudolf Kunz. And his idea is we have to allow for efficient and safe sharing of memory among multiple programs. So just like your computers are doing now, you're not just running one program at any given moment, right? You have to run multiple programs. So whenever the operating system is going to control which programs are going to be running on your computer at a given moment. So you have to be able to perform memory sharing because there's only a certain amount of memory. So you have to make sure that pages are allocated in order to maintain high performance and for so you don't have one program overwrite another program's data. The second is remove the program burdens of a small limited amount of main memory. So for example, 16K, then you don't have to say, well, you know, you can only code those programs that can hold 16 kilobytes of memory. As you can imagine, that's not very big. So you can take advantage of swapping back and forth in order to do this. So a program's address space, so we have this memory, right? So we have data memory, right? So I've been telling you about this box, and then we have this kind of tiny little cache, level 3 cache, and then we have this physical storage, right? And so the address space of a program is indicated, runs one program, this runs another program, this runs another program, and so forth. So the address space is a separate range of memory locations accessible to only one specific program. The virtual memory is important in ensuring that we don't overwrite another program's data. And the physical address is the physical location in main memory of the program. So this is its physical location in the main memory. We have 2 to the 32 values in the data path, but we have to access level 1 cache. This is what the 16 kilobytes is. So how do we map this large program to this small amount of memory? So we'd be swapping out portions of this program in order to do it. And that's known as a page. A page is a fixed-length continuous block of virtual memory. It is the smallest unit of data transfers between the main memory and the non-volatile storage. I should indicate that that's the end of the teaching. You know, right here, 7.5. A page is similar to a block. Actually, I explained this to you already about how a block in cache is the smallest unit you can transfer between cache levels, whereas a page is the smallest unit you can transfer between the main memory. So that's the difference in notation there. And so a page fault is what happens when I'm the data path and I'm accessing the cache, right? It's not in level 1, 2 cache, it's not in level 2 cache, it's not in level 3 cache, right? We have cache misses here. So now I have this level of main memory before we access the physical disks, right? Where that contains our page for the processor. Is it there? Nope. That's a page fault. The page fault, think of page fault as the equivalent at the main memory level as a cache miss is at the cache memory level. And cache means you have to swap faster pieces. Main memory, you have to go through the operating system. Now, how do we actually do this address translation? So virtual address is an address that corresponds to a physical location, to a location in the virtual space, and is translated by address mapping to an address space. So I'm going to show you a diagram to describe how that means. I have this address here, and I need to actually translate. I have a certain amount of memory blocks, and a certain amount of memory I can actually access. And in almost every case, you will have more bits in your address. So you need to actually translate that to get the proper value. So that's what's known as a virtual address. So here, it's kind of a basic diagram. So you have a virtual address, which is what's generated by the processor. And what happens is, as you're swapping pages in and out, the operating system is going to try to find the most efficient place to put it. There's no guarantee that the program is going to have them all on the same row. So there's no guarantee that you start instruction 0, instruction 1 here. You're just trying to swap them out based on. So if you're using, let's say you're using 2 functions a lot, odds are good they're going to be closer up here because they're going to be used quite a bit. Whereas something in the program that was used at the beginning and wasn't used again, it's going to kind of drop down here. So what happens when it's actually in the physical space as opposed to the disk address? And we're going to discuss this, and this is where we're going to end the lecture. So we're going to go through 7.10. Was 6.21 through 7.10, and then example question 7.1. Okay, so the page offset number is just determined by log 2 by the page size. So I've 2 to the 10 is just going to be 10 bits to indicate how big it is. The virtual page number is determined by the address size minus the page offset. So that's dismiss you guys in 3 minutes. So, and then the physical page number is determined by the actual physical size of the memory. So this example question will describe how this works. So example 7.1 is, given a 32-bit MIPS data path, where the page size is set at 4 kilobytes, so that's the minimum amount of size we can transfer back and forth, it's 4 kilobytes. The number of physical pages allowed in memory is 2 to the 18. Show how virtual mapping is performed, and how big is the physical memory. So 4K is actually 4096, and so log 2 of 4096 is 12. So the first 12 bits on the virtual address is the page offset. So you can see you can already see the diagram a little bit. 0 through 11 is the page offset. This is the equivalent at this level of your byte addressing. You shift left 2. Here, you're actually using these 12 bits to indicate the page offset. Then, log 2 to 18 is just the next 18 bits to indicate the number of actual pages, right? So that tells me where the address is. So what that means is 12 plus 18 is 30, right? So that means the actual physical amount of memory that I have is 2 to the 30. But I have 2 to the 32 bits, right? And so what we do is we combine the concept of this diagram where I have 32 minus 12 is 20, right? Maps to 18 here, right? And the operating system can put them in out of order. So what happens is we have 31 to 12, which is the 20 bits in the virtual page, is translated using this process into a physical page number of 12 through 29, because that's 18. We started at 11, so now we get to 29, which means the physical size of memory is 2 to the 18 plus 12. 2 to the 18 plus 12 is 2 to the 30, which is 1 gigabyte. So here's what it works. I'll go over this one last time and then I'll dismiss you. What this means is the smallest amount we can transfer between any sizes. For 4 kilobytes, that's 2 to the 12. So that means this is the smallest size. We want to increment by 1 in the next page. We actually have to increment by 2 to the 12, right? Find that address, because each page contains this amount of memory. Now, in the virtual memory, which is the address generated by the processor from a load word instruction or a store word instruction, we have these 32 bits, right? So that's fixed. We use this translation because we can't guarantee that they're going to be in order, and that's done. We're going to be learning this next class using a page table and transition loci buffer into, where is it? Okay, so to the 18 is the actual number of pages. So this is actually the location of the physical page in the main memory. So this translation allows us to find that. So therefore, by 18 plus 12 is 30. 2 to the 30, that's the amount of physical memory. Does anybody have any questions before I dismiss you? Okay, you are dismissed.